Hello viewers, we shall continue our discussion on the architecture and organization of 8085. In the last lecture, we have introduced several aspects of the architecture and organization of 8085. We have discussed the ALU, the capabilities of the ALU. We have discussed the interface section, various lines which are provided for interfacing memory and input-output devices. If ALU is the brain of the system of the CPU, then the timing and control unit is the heart of the CPU. So, today we shall discuss in detail the timing and control unit, which is heart of the central processing unit. Just like heart pumps blood to other organs of the body, similarly the control timing and control unit sends signals, various types of control signals, to keep various subsystems alive and in working condition. So, as I told, the timing and control unit essentially coordinates and controls the subsystems within CPU such as ALU, the memory, the registers, and also outside the CPU like memory and input output devices. In your computer architecture class, you may have studied the design of control unit. As you know, control unit can be designed in two ways. One is known as hardwired, second one is microprogrammed. But irrespective of whatever way it is designed, the function is same. It is a sequential circuit which receives input, various inputs like instruction, information about the instruction, interrupts, DMA requests, and so on, and generates various output signals. And of course, it is done sequentially under the control of a clock. So, this is the control unit, timing and control unit, you can say. We shall first briefly discuss about this clock. You may have some idea about the clock. I shall very briefly discuss by what do you mean by clock, what it is, what are the different types, and how it is generated inside the microprocessor. Clock can be single phase, or clock can be of two phases, two phase clock or single phase clock. Let us see what we mean by single phase clock. A single phase clock will have this kind of repetition of signal. It can be characterized either by two levels. This is your high level and low level, or sometimes it is characterized by two edges. This is your high to low, and or by this edge, that is low to high. In other words, as you can see here, it has got two states, high or low, or two transitions, high to low, low to high. So, various operations are performed whenever either the clock is in high level or low level, or whenever there is a transition from high to low or low to high. So both happens. So this is the single phase clock. On the other hand, a two phase clock will have two clocks, two signals. One is known as phi 1, another is known as phi 2. This is your, let's assume this is your phi 1, and another signal like this. The important characteristic is that neither the phi 1 and phi 2 are not simultaneously 1, as you can see here. So that means whenever phi 1 is low, phi 2 is high. When phi 1 is low, sorry, whenever phi 2 is low, phi 1 is high. In other words, it has got, if you look carefully, it has got three states. Both can be high, low, low, high, high, low, but you will not find states where when both of them are high. There are some locations where it is simultaneously low, but you will not find both of them are high simultaneously. That means it has got three states. Three states, by that I mean uh, low, high, high, low, and low, low, but it never becomes high, high together. That's how it is. Both of these clocks are non-overlapping because the ones are not overlapping. Then there is another important parameter, that is your time period. That is true for both single phase and two phase clock. So if T is the time period, then f clock frequency is defined as 1 by T. So T can be either in second, millisecond, nanosecond. Nowadays the time period is usually specified in nanosecond because clock frequency is so high that it is specified in nanosecond, and frequency can be stated in hertz, megahertz, gigahertz, like that. Now how this clock is generated in case of microprocessors? It is possible to generate the clock externally, then apply it to the microprocessor. Another alternative possibility is that the clock circuitry is inside the microprocessor, but some component which cannot be fabricated within the IC has to be kept outside the chip. For example, in case of 8085 microprocessor, that quartz crystal which is necessary for crystal oscillator is has to be connected from outside. On the other hand, the other parts of the circuitry, electronic part of the circuit, oscillator, is inside the chip. So only external component that you require is a crystal, quartz crystal of some frequency, and some few capacitors, so that the quartz does not oscillate at harmonic frequency. So in case of 8085, the situation is like this. So this is the 8085. Inside the 8085, you have to connect a crystal, quartz crystal, and these two pins are X1 and X2, and you have to connect one capacitor to this end, small value of capacitor, 10 picofarad or some value like that. And inside the chip there is a oscillator, some kind of feedback is there. As you know, for oscillation you require positive feedback, and to generate two phase clock which is required internally, a flip flop is used, T flip flop. This is your Q, this is your Q bar, and you get phi 1 and phi 2. So although externally you are applying a crystal, only a crystal, inside the chip we are generating two phase clock. Two phase clock has many advantages, and particularly in the realization of VLSI circuits, you will see that two phase clock is widely used, and in this class obviously we don't have scope to discuss the advantage of two-phase clock, but if you attend a course on VLSI circuit, all these thing you will learn. But just for your information, inside the chip we are using two-phase clock, but to outside you get only one-phase clock, that is your clock. Of course, it is available through an inverter. So there is a pin called clock on the microprocessor. There are two pins, X1 and X2, where you can connect the crystal, and through this clock pin you get clock which is generated internally for external use. So this is how it happens in case of your 8085. So this is within the chip and this is external to the chip. This side is external to the chip and this part is within the chip. So this is how clock is generated in case of 8085 microprocessor. Now under the control of the clock, the instructions are sequentially fetched from the main memory one after the other, and it is executed within the CPU, and that happens under the control of a clock. And we can say that instruction cycle, that is time required to execute one instruction, can be broadly divided into two cycles. One is fetch cycle, fetching an instruction from the main memory, then decoding it, and after that execution cycle. So fetch cycle will require several clocks, we shall discuss it. Execution cycle will also require some clocks, a number of clocks, and obviously the number of clocks that is required for fetch cycle is usually fixed, as we shall see. But execution cycle, the total number of clocks that you will require will depend on the particular type of instruction. So that part is variable in time. The time required will depend on the instruction that has to be executed. So instruction cycle involves two different cycles called fetch cycle and execution cycle. Now execution cycle, as I told, will have different variations. It will have variable time. Execution cycle will be variable in time because for execution you may have to fetch some operands from the main memory. So or you may have to write some data which is generated after execution of the instruction into the memory. So execution cycle will involve some read cycles, one or more read cycles, or it may involve one or more write cycles. You can say that execution cycle will involve read cycle one or more, write cycles one or more, or some combination of them. And we shall discuss in detail how this happens for different instructions. Inside the chip, how actually fetch cycle happens. As we know, this is the internal circuitry of a microprocessor. You have got some internal bus, and as we know, there is ALU, there is instruction register which is connected to the internal bus. There are a set of registers, as we discussed earlier. There are general purpose registers B, C, D, E, H, L, stack pointer, program counter. Then you have got one instruction decoder, and you also this instruction decoder output will go to the control unit, timing and control unit. So here is your control unit. How it happens? As we know, the instruction to be executed next is available inside this program counter. So from the program counter it goes to the external world, to the main memory. So it is sent to the main memory through the uh, system bus, that is your address bus. And let's assume this is your main memory, and main memory is accessed in the form of locations. That means address location is specified here, and let's assume it is pointing to this. Let's assume here it is, say db is the value which is the instruction to execute. Now this will be read. The control signal will generate control signals like read, and in response to this the main memory will output this data, say db, that will go to the system bus. So sequence of events starts in this manner. First the program counter generates the address, it goes to the main memory through the external bus, then the data is read, and this is your data bus, and through the data bus it goes to the internal bus of the microprocessor. This part is inside the chip, and then it goes to the instruction register IR. It is decoded, control unit generates the control signal, so it does the other operations. So in this way the instruction execution take place. So the address is generated by the CPU, and accordingly the control unit generates various control signal. Here control signal is shown only for the main memory, but it generates signals for all the different parts, the register for controlling registers, for controlling ALU, and so on. So in this way the phase cycle is executed. Now let us see how it is done in terms of clock cycles. Say this is the clock which I have shown, which is coming out from that microprocessor, this clock. I am referring everything with respect to this clock. So this is the clock which is generated internally and made available to the outside world. Inside it is CPU, two phase, but this clock is one of the two phases. Now the CPU generates all the memory and IO control signals like a address information which will be necessary for getting the data from the main memory. So address is generated, this is the higher order bit address, that means PC 8 to 15 program counter value 8 to 15 is available on these lines. Then program counter value 0 to 7 is available on these lines, but it is available only for T1 clock cycle. One clock cycle which is designated as T1, and during this period there is a signal known as address latch enable is also generated, ALE. ALE is generated, and that means whenever ALE is generated, this corresponds to the lower, or this the whatever value is available on AD 0 to 7 corresponds to the lower order bit of the address. So the outside world gets higher order bit of address through PC 8 to 15 and lower order bit through this AD 0 to 7 lines. And of course the other signals like IOM, S0, S1, these are all generated simultaneously during this period. In response to this, the main memory will respond with the instruction, and it will be available on this same data lines. So after some time you get the instruction which is available on the data bus. Now it is data. So here it is your instruction which is fetched from the main memory, and this reading operation is done with the help of this read signal. So with the help of this read signal, the read operation, this instruction is read into the main memory. That means the instruction is transferred from this bus. This is your data bus AD0 to 7. From the data bus, it goes to the instruction register where it is decoded, and the control unit performs other functions. Obviously, this value of IOM S0 and S1 will be different for different types of machine cycles. In case of instruction fetch, which is taking place from the main memory, this value will be IOM will be 0, because this access corresponds to main memory. However, your S0 will be 1 and S1 also will be 1 in case of your instruction fetch. Okay, so this is how instruction fetch will take place in case of under the control of the clock. And instruction fetch is completed, as you can see, within 3 clock cycles, T1, T2 and T3. Within this, the instruction is going inside the inside the CPU. Then inside the CPU, the decoding is done during this 4th clock cycle, T4. And if no operand fetch is necessary from the main memory, instruction execution can be completed during this clock 4, T4. That means, suppose you are performing execution of 2 register operations. Say the one operand is in accumulator, another is in register B. There is no need to fetch anything from the main memory. So that operation can be performed within this clock cycle. So instruction execution may be completed just in one machine cycle or in 4 states. So this is known as state 1, state 2, state 3 and state 4. So this is one machine cycle, and in this particular case the machine cycle involves 4 states. Particularly for instruction execution, this fetch cycle you will require 4 states. So machine cycle number 1 and 4 states is the minimum time that you require to execute an instruction. However, if it requires to fetch operands from the main memory, then you have to perform read operations, or say after calculation, if you have to store the data into the write into the main memory, again you have to perform write operations. So it will involve one or more read or write cycles, and this is done in this manner. A read cycle, as you can see, the clock, the lower higher order bit address, we see 8 to 15, then your PC 0 to 7 are generated here. Here you are reading the data under the control of the clock. During T1 you get the address of the operand, and during T2 and T3 you get the data. So for read operation you require 3 states or 3 clock cycles. Similarly, as you can see here, read operation is performed during this period. So you are reading this data under the control of this read signal. Similarly, the write cycle can be completed in three states or 3 clock cycles. And during write cycle, the write signal is, as you can see, write signal is activated. During read operation, read signal is activated by the CPU. So this is how read and write operations are performed. And a particular instruction execution may involve one fetch cycle like this and few read or write cycles. and later on when we shall discuss instruction execution in more detail, we shall see how these various machine cycles, fetch cycle, read cycle, write cycles are combined together to execute different instructions. Now, this is so far as the instruction execution is concerned. We have seen that CPU is interacting with the memory and input output devices. So, it is performing reading of the instruction from the main memory, reading operands, writing result into the main memory. Apart from that, we have seen that microprocessor is provided with various CPU and bus control signals, and one important CPU control signal is the interrupt. And as you have seen, the microprocessor 8085 microprocessor is provided with a number of interrupt signals. In other words, the microprocessor 8085 has a very powerful interrupt structure. In this diagram, the hardware interrupts which are provided by 8085 is nicely depicted, summarized. So, let me explain the interrupt structure of 8085 with the help of this diagram. There are, as you have seen, there are 5 interrupts: trap, RST 7.5, RST 6.5, RST 5.5 and INTR. Trap, RST 7.5, RST 6.5, RST 5.5 and INTR. So, you have got 5 interrupts, out of which this trap is non-maskable. It cannot be masked, non-maskable. So, this is a non-maskable interrupt. That means, if it comes from any external source, CPU will be interrupted. What do you really mean? Whenever the CPU gets interrupted, it will start executing the instruction it was executing. That means, control flow of the instruction execution will change. Wherever it was executing, it was fetching and executing an instruction. It will complete that execution of that instruction. After that, it will branch to a particular memory location. That memory location is specified for trap, it is 24H. It is called vector address. Why it is called vector address? Because it is fixed. Whenever this interrupt occurs, it will always, the program counter will be initialized by this value 0024H. And what will happen to the program it was executing? That program counter value will be stored in the stack. So, this location 0024 will be essentially the address of the interrupt subroutine, interrupt service subroutine. That means, the interrupt service subroutine corresponding to trap will start from memory location 0024, and after that subroutine execution is over, then it will return from that subroutine, and program counter value which was stored in the stack will be recovered, and program counter will be initialized by that value. So, this is how the processor will respond. Now, this is the case of non-maskable interrupt. Now, as you can see here, this particular sensitivity which is shown here, this trap is sensitive to both level. That means, if that line goes to high level, trap will be activated. If there is a low to high transition, even then this trap will be activated. That means, trap input is sensitive both to high level as well as to low to high transition. This particular diagram shows that. And so, since trap is non-maskable, it has got the highest priority, priority number 1. On the other hand, the other interrupts like RST 7.5, 6.5, 5.5 and INTR, they have lower priorities. So, second highest priority is RST 7.5. What do you mean by the priority? By priority we mean, suppose RST 7.5 and RST 6.5 are activated simultaneously. So, which one the CPU will accept? It will depend which one has the higher priority. So, depending on which one has the higher priority, that will be activated. And as I was telling that 2, 3, 4 and 5, all these are maskable interrupts. That means a programmer can disable all these interrupts by setting separate flag bits. How it is done? As you can see here, there is a enable interrupt and disable interrupt. These are instructions. With the help of this, you can disable the entire interrupt systems. That means if this is low, then none of these interrupts will be activated if this is connected to all. So, if it is enable interrupt, it is set, then it is 1. On the other hand, whenever you execute disable interrupt, or if there is any interrupt, if any interrupt is recognized, then automatically the interrupt system is disabled, and then this line is 0. That means none of these interrupts can be activated. So, interrupts, all the interrupts can be disabled by executing an instruction known as disable interrupt, and all these interrupts can be enabled by executing an interrupt known as instruction known as enable interrupt. EI is enable interrupt, DI is disable interrupt. Moreover, these interrupts have several, separate masked bits. They can be selectively masked. So, using enable interrupt and disable interrupt instructions, you can disable all the interrupts or enable all the interrupts. But what you can do, if you want, you can enable the interrupt system, but you want to disable some of them selectively. That also can be done by programming these values. There are some mask bits. These mask bits are provided inside the CPU, which can be programmed by using an instruction known as SIM, set interrupt mask. There is an instruction known as set interrupt mask, SIM, with the help of which these flag bits can be set or reset, and that way you can selectively enable or disable these interrupts. Clear? Now, as you can see,
interrupt enable, that is master interrupt enable.
yeah, that enable interrupt enables all the interrupts, or disable interrupt disables all the interrupts, but using these mask bits you can selectively enable or selectively disable. That is the point. So, now you can see the sensitivity is also different for different interrupts. For example, for RST 7.5 it is edge sensitive, for RST 6.5, 5.5 and INTR, these are all level sensitive. Now, whenever an interrupt occurs, whether it will be activated or not will be dependent on two things, as you can see. First of all, whether this line is 1. 1 means unless enable interrupt is active, it will not be 1, or this mask bit is 1 is 0. If it is 1, then it will be deactivated. So, if it is 0, then it is 1, input is 1, so it will be active. That means this should be 1, this should be 1, only then this enable will be activated. So, it is necessary that enable interrupt should be active, mask bit should be 0, so that this interrupt is activated. And since it is edge sensitive, that is why you require a flip flop to store the information. If it is level sensitive, then you do not require a flip flop here. And in case of RST 5.5, 5.5 and INTR, as you can see, this kind of flip flop is not there, and so it is level sensitive. The level should be high to activate RST 6.5, 5.5 or INTR. So, in all these cases, as you can see, it is necessary that enable interrupt is active and mask bit is 0 for that particular interrupt to be applied to the microprocessor, to be accepted by the CPU. Is it clear? Now, in case of trap RST 7.5, RST 6.5 and 5.5, you can see there are fixed addresses where the program counter will be initialized 0024, 003C, 0034, 002C. On the other, these are known as vector addresses because whenever interrupt occurs on any of these lines, the processor will jump to these fixed locations. But in case of INTR, there is no fixed address. That address is supplied by an external device known as interrupt controller. Later on, whenever we shall discuss the interrupt driven data transfer, you will see you will require a special device known as interrupt controller, and that interrupt controller will provide the address where the CPU will jump whenever this INTR interrupt occurs. So, primarily INTR uh, has to be used along with a interrupt controller hardware. So, we shall discuss it later on in more details. Now, apart from the interrupts, there are some more bus control signals like hold, which is a DMA request. So, whenever a DMA request occurs from some external device, what the CPU does? CPU will immediately uh, generate one hold acknowledge signal, and this is your DMA request from some external source, direct memory access request. And in response to this, the CPU will generate another signal, that is your HLDA, hold acknowledge, which is essentially DMA grant. That means direct memory access has been granted to the outside world. What does it mean? It means that whenever this HLDA is active, the all the uh, addresses, that means address lines, data lines, and control lines are tri-stated. That means CPU relinquishes its control over the system bus. Now, one external device has to take control of the system bus, and whenever DMA mode of data transfer will be discussed, you will see that an external device known as DMA controller will take control of the bus and will perform the DMA mode of data transfer. So, this is what happens in case of this DMA request. Uh, the response of the processor is to generate a DMA grant signal, and it tri-states all the buses so that an external device can gain control of the bus for DMA mode of data transfer. Apart from this, there is another CPU control signal, that is your reset, and in response to reset, what the CPU does, what is the purpose of reset? You may have seen whenever you are executing a program, the computer hangs. What do? You depress the reset button. By that, what actually happens? The CPU is brought to a predefined state. What do you mean by that predefined state? What the CPU does, it initializes certain registers, flip-flops with some values. Some flip-flops are resetted, set to 0, some are set to 1. Let us see what happens in case of 8085. How 8085 performs the reset operation. Whenever you depress the reset button, make it 0, then the CPU, what it does, it clears program counter. That means program counter is set to all 0. So, whenever you reset it, the program counter is set to all 0. That means the execution will immediately start from all 0 location. If you reset it, it is brought back to a predefined state. It will also reset the instruction register. It will reset the machine state flip-flop. have seen that the inside the timing and control unit has got some flip flops with the help of which the state of the machine in whether it is in T1 or T2 or T3 or T4, that information is stored. So, this is also resetted. Then machine cycle flip flop is also resetted, and it also sets certain flip flops like RST 7.5 mask bit, RST 6.5 mask bit, RST 5.5 mask bit. These are all resetted with the help of this uh, mask bits. I think I have given a wrong information. There is no mask bit for INTR. So, please correct it. There is no mask bit on for INTR. There are only 3 mask bits. That means that INTR can be disabled by using only disable interrupt instruction, and enabled by using enable interrupt instruction. For other 3 interrupts, there are mask bits, but there is no such mask bit for INTR. So, these are the responses of the microprocessor. Now, as you have seen, the 8085 timing and control unit or any timing and control unit is nothing but a sequential circuit. How its operation can be explained? With the help of a state transition diagram. You have studied sequential circuits. How the behavior of a sequential circuit is explained? With the help of a state transition diagram. And in case of any microprocessor, the control unit is a very complex sequential circuit. It will have a very large number of states, and obviously the description of the entire operation with the help of a state transition diagram is very complex. We shall try to explain a subset of the operation with the help of a state transition diagram of 8085. Even the simplified state transition diagram looks like this. How it works? Whenever you reset, it goes to a state known as T reset. We have seen what happens whenever you reset it. So, it goes to a state T reset. After that, it starts fetching and executing instructions. As you know, it will start fetching instructions from all 0 locations, 0000 memory location. So, it will go to that T1 clock cycle of the instruction fetch cycle. Now, what can happen later on? You may have executed one halt instruction, then it will go in this direction, but we shall not discuss it right now. Normally, whenever you are resetting, immediately after that, obviously halt instruction will not be executed. So, it will go to T2. Now, it will go to T2 and before going to T3, it will check 2 things. It will check whether there is a ready signal activated or not. As we have explained, the ready signal is used to interface slow memory and input output devices. So, some additional clock cycles are introduced in between T2 and T3. We have discussed about the read and write cycle. So, if the memory devices are slow, then in between T2 and T3 some wait cycles will be introduced, which are known as T wait. Later on, when we shall discuss interfacing of memory, particularly slow memories, we shall see how wait cycles are introduced. So, this diagram shows, this state transition diagram shows how this really happens. That means, after T2 it goes to this T wait, and it will remain in that wait cycle. It will keep on generating that wait cycles until the ready signal is withdrawn or ready signal comes from the memory or input output devices. And whenever the ready signal comes, or there is a uh, then it checks whether there is a DMA request. After T2, it checks whether there is a DMA request. If there is a DMA request, it sets the DMA hold acknowledge flip flop, hold acknowledge flip flop, and then it goes to T3. If something is missing, it will go to T3. It goes to T3. Then after T3, if it is a first machine cycle, that is instruction fetch, it will go to T4. If it is not the first machine cycle, then obviously it will bypass and it will go to this line. If it is the instruction fetch cycle, it will require 4 clock cycles, but if it is memory read, memory write, then 3 clock cycles are sufficient, then it will go here. Then if it is a instruction fetch cycle, it will go to T4, and after T4 it will check whether a particular instruction requires 6 clock cycles. There are few instructions which requires 6 clock cycles in the instruction fetch cycle, and if it is true, then it will go to, again it will check hold signal DMA request or not. Then after that it will set that hold acknowledge flip flop, then it will go to T4, T5 and T6, 2 more clock cycles, then it will come out. And if the hold acknowledge flip flop is set, then it will go to hold state. Hold state means it will try state the buses and remain in that condition until that DMA request is withdrawn. It will remain in that state, and whenever there is no DMA request, it will check whether it is the last instruction of the machine cycle or not. If it is the last instruction of the machine cycle, it will check whether there is any valid interrupt or not. If there is no such, if it is not the last instruction of the machine cycle, then it goes to, if it is not the last machine cycle of the instruction, it goes back to T1. That means another cycle is started. If it is not so, then it goes to, if it is the last instruction machine cycle of the instruction, then it checks the valid interrupt. So you see here what it is doing, it is checking whether you have reached the last machine cycle of the instruction or not, and it checks whether a valid interrupt has occurred or not at the end of the last machine cycle of the instruction. What does it mean? It means that the checking of the instruction occurrence by the CPU take place only after the end of the execution of each instruction. On the other hand, DMA request, say here you are checking, here you are checking much before that. So if somebody asks you a question that there is a DMA request and interrupt request, both have come together, which one will be accepted? Obviously the DMA request will be accepted first, because it is checked much before. Even before the execution of an instruction, it is being checked and it goes to the hold state. But only at the end of the execution of each instruction, the interrupt is checked, and if there is an interrupt, then it sets that interrupt flag bit, interrupt acknowledge flag bit, resets that interrupt enable flag bit, and it goes to execute an instruction. Let's now consider the other parts which we have not yet discussed. If there is a DMA request, it will continue to remain in this particular state known as T hold, and it will reset the hold acknowledge flip flop, and only when that is withdrawn, that means hold acknowledge is withdrawn, hold signal is withdrawn, it will come out of it, it will reset that hold acknowledge flip flop. But if it will also check whether it was halted or not. Suppose in between one halt instruction was executed, halt is 7.6, And suppose you have written a program of 10 lines. At the end of those 10 lines, you should write one instruction known as halt. The reason for that is so that the subsequent instructions, subsequent part of the memory locations may be garbage. You have not written anything, are not executed. So you will write halt. Halt means the CPU will not fetch those garbage memory locations and try to execute. And so if halt instruction has been executed, it will go to that halt state, and it will come out of the halt state in three situations: whenever there is a valid interrupt or there is a DMA request. And you can see here, if there is a DMA request, after performing that DMA operation again, it will come back to the halt. So only way the CPU goes out of the uh, halt state is with the help of a valid interrupt. That is why in some cases it is also known as wait for interrupt. It waits for interrupt. So after it comes out from the halt state, it resets the hold acknowledge flip flop, sets interrupt acknowledge flip flop, resets INT flip flop, and goes back to the T1 state. So from this state transition diagram, one thing is clear, that CPU continuously performs execution of instructions one after the other with the help of uh, different machine cycles and clock cycles or states, and in between, if there is an interrupt request, if there is a DMA request, accordingly it performs certain operations, and it either goes to hold state or halt state depending on there is a DMA request, or if you have executed one halt instruction, and so on. So, we have discussed in detail the time function of the timing and control unit of the 8085 microprocessor, and we have seen how instructions are executed with the help of a 8085 microprocessor. In the next class or next lecture, we shall cover the instruction set architecture of 8085. Thank you.
Sir, what is the DIMC signal?
That is actually DIMC is getting the name, bus idle machine cycle. Bus idle machine cycle. You know, there are some cycles when the bus remains idle, that means it is in a hold state, bus idle machine cycle.